What is the coldest temperature possible in the entire universe? And if we keep cooling a substance lower and lower, can its entropy continue to decrease forever, or is there a fundamental limit? Could we eventually make its entropy exactly zero, and if that were possible, what would happen when a substance reaches the coldest temperature physically allowed by the laws of nature? Absolute zero. Today, we're going to uncover the third law of thermodynamics and answer these fascinating questions. Remember from the last episode, if entropy can increase with temperature, can it also keep decreasing as we cool a substance? And if we continue cooling, what is the smallest possible value entropy can have? To answer that, let's first understand what really happens when an object becomes colder. Take a metal block at room temperature, although it looks perfectly still. But every atom is constantly vibrating about its fixed position. These vibrations are a form of thermal energy. Now imagine placing that metal block inside a freezer. As heat leaves the block, its temperature decreases, and as the temperature decreases, the atoms vibrate more slowly. Cool it even further and those vibrations become even smaller. The colder the object becomes, the less thermal motion its atoms possess. So, it's tempting to think, if we keep cooling forever, won't those vibrations eventually disappear completely? To answer these questions, we first need to understand one of the most extraordinary temperatures in the universe, absolute zero. But what exactly is absolute zero, and why is it so special? As we know, temperature is a measure of the average kinetic energy of the particles in a substance. In simple words, the faster atoms and molecules move, vibrate, and rotate, the higher the temperature and higher the entropy. And as they lose energy, their motion gradually slows down, which results in lower the entropy. This process continues until we approach the lowest temperature that the laws of physics allow. This single point, the theoretical temperature at which a substance has this perfect minimum entropy arrangement, is what we call absolute zero. And on the Kelvin scale, that's 0 Kelvin, or minus 273.15 degrees Celsius. Now, here's where things become truly fascinating. If the particles are moving less and less as the temperature drops, you might expect that at 0 Kelvin, all motion would stop completely. And if all molecular motion stopped, wouldn't there be only one possible arrangement of the particles? Would that mean the entropy becomes exactly zero? For nearly a century, questions like these fascinated physicists around the world, and the answer eventually led to one of the fundamental laws of thermodynamics, the third law of thermodynamics. The third law states, the entropy of a perfect crystal at absolute zero is zero. At first glance, this may seem like a simple statement, but every word in that sentence has a very specific meaning. Perfectly crystalline. The substance must have flawless internal order. Every particle is exactly where it should be. No defects, no irregularities, no impurities. Absolute zero. The temperature must be exactly 0 Kelvin. Entropy is zero. Under these two conditions together, there is exactly one possible microscopic arrangement. Zero randomness, zero disorder. This idea is far more important than it might seem. For the first time, thermodynamics has an absolute reference point for entropy. Just as sea level serves as a reference for measuring altitude, the third law provides a fixed reference from which the entropy of all other substances can be determined. But one question still remains. Why does having only one microscopic arrangement make the entropy exactly zero? To answer that, we need to revisit an equation we explored in the previous episode, Boltzmann's famous entropy equation. His famous equation is S equals K natural log W. Now, imagine a perfect crystal. Every atom occupies its exact position in a perfectly repeating pattern. As the crystal is cooled closer and closer to absolute zero, thermal motion becomes smaller and smaller. In an ideal perfect crystal at 0 Kelvin, there's only one possible microscopic arrangement. In other words, W equals 1. Substituting this into Boltzmann's equation gives S equals K natural log of 1. And since the natural logarithm of 1 is 0, entropy becomes 0. This is why the entropy of a perfect crystal at absolute zero is defined as 0. Before the third law, we could only ever talk about a change in entropy between two states. Now, for the first time, we have an absolute 0 point to measure every other entropy value. So far, here can slightly mind-bending question. Can we simply build a strong enough refrigerator and cool something down to exactly 0 Kelvin? The answer gives shocking surprise. We can't. According to the unattainability principle, it is impossible to reach absolute 0 using any finite number of cooling processes. We can get incredibly close. Scientists have cooled atoms to temperatures just billionths of a degree above absolute 0, but reaching exactly 0 Kelvin is impossible. You can think of it like walking toward a wall while each step is only half as long as the previous one. You'll get closer and closer, but you'll never actually touch the wall. In the same way, every cooling process brings us nearer to absolute 0. This is why the record for the coldest temperature ever achieved in a lab is still a tiny fraction of a degree above absolute 0. Incredibly close, but never, ever, exactly 0. Now, you might be thinking, this sounds like a purely theoretical curiosity, but the third law has real, practical importance. Absolute 0 provides a reference for measuring absolute entropy, which is essential in predicting reaction spontaneity, something we'll build on when we study Gibbs free energy calculations in later chapters. It explains cryogenics, the science of super low temperature research, and why fields like superconductivity, where materials conduct electricity with 0 resistance, only appear as we push temperatures closer and closer to absolute 0. And it even connects to cutting-edge research like quantum computing, where quantum processors need extremely low temperatures, just above absolute 0, to function correctly. So this purely theoretical law is quietly running in the background of some of the most advanced technology being built today. Let's quickly recap today's journey. As a substance is cooled, the motion of its particles decreases. At absolute 0, an ideal perfect crystal has only one possible microstate. According to Boltzmann's equation, that means its entropy is 0. And although absolute 0 can never actually be reached, the third law provides the fundamental reference point for understanding entropy in thermodynamics. The first law taught us that energy is conserved. The second law revealed the direction of natural processes. And today, the third law showed us the lowest possible limit of entropy. Together, these three laws form the foundation of thermodynamics and help us understand everything from melting ice and cooling coffee to superconductors and the behavior of matter at the coldest temperatures in the universe. But have you ever wondered, what exactly is temperature? The answer lies in a law that forms the very foundation of temperature measurement, the 0th law of thermodynamics. We'll uncover that fascinating idea in the next episode. If you enjoyed this video, don't forget to like, subscribe to Decoding Education, and share it with someone who's curious about science. I'll see you in the next episode.